Welcome to the RobotStudio tutorials. In this session, we'll explore how to add joints between rigid objects in RobotStudio to enhance physical simulation. RobotStudio supports 5 types of joints. Joints act as constraints that define how two rigid bodies can move relative to each other. A rotational joint enables rotation around a single axis. A prismatic joint allows linear movement along an axis. A cylindrical joint allows both rotational and translational movement along an axis. A ball joint permits rotation in any direction around a fixed point. A lock joint restricts all movement, effectively bonding the two objects together. We'll begin by creating a hinge using a rotational joint. First, ensure that the connected parts have physics behavior enabled. Set them to dynamic. Collisions between objects connected by joints are ignored in the rigid body simulation. To manage this, we can introduce intermediate parts connected by lock joints. Here, we use lock joints to attach knuckles to hinge plates. In this case, the position of the lock joint is not critical. You can view and manage joints in the Physics browser under the Modeling tab. For the rotational joint, specify the connected parts and define the rotation axis. Use Snap Mode Center to select the center of the knuckle. A preview of the rotation axis will appear in the graphics window. Click Create to generate the joint. Test the joint by dragging the connected parts to observe the motion. You can also right-click the rotational joint to access and modify its properties. RobotStudio provides comprehensive options for defining joint characteristics, enabling advanced simulations and precise control of rotational joints. Let's explore these configurable properties that replicate real-world mechanical behavior. Here we have motor properties which define how the joint behaves when driven by a motor. This includes desired speed, which is the target rotational speed of the joint. It's the speed the motor tries to maintain. Then we have max torque, the maximum torque which the motor can apply to move or hold the joint. This limits the motor's strength. Then we have limits. These restrict the joint's range of motion and torque. We have minimum limit and maximum limit. These represents the angular range within which the joint can rotate. Beyond these limits, the joint cannot move. Then we have max torque, which is the maximum resisting torque applied when the joint reaches its limit, simulating a hard stop. Next, we have spring properties. These simulate elastic behavior, like a spring attached to the joint. We have desired position, which is the angle where the spring wants the joint to rest, its equilibrium point. Then we have max torque, which is the maximum torque the spring can exert to pull the joint back to the desired position. Next, we have damping, which is the resistance to motion, reducing oscillations and stabilizing movement, like shock absorbers. Last, we have elasticity, which defines how stiff the spring is. Higher elasticity means stronger pull toward the desired position. Then we have friction properties. These simulate resistance due to friction. We have friction torque, which represents the amount of torque opposing motion, simulating friction in bearings or surfaces. Higher friction means more resistance to movement. That concludes the overview of all configurable properties for the rotational joint. Next, we'll move on to creating a prismatic joint. Since we've already defined our device and its moving part, set the device base as fixed and the moving part as dynamic. Then, navigate to the Modeling tab and click on Physics Joints and select Prismatic Joint. Specify the two connected parts and define the axis of translation. A preview of the translation axis will appear in the graphics window. Click Create to finalize the joint. Once created, test it by dragging the dynamic part. You can also right-click the prismatic joint to configure its translational properties, similar to how we did with the rotational joint. Next, we'll create a cylindrical joint. A cylindrical joint allows both translation and rotation along the same axis, making it ideal for tasks that require sliding and rotating in one direction. In this example, we've prepared parts that represent a cylindrical joint. The vertical gray rod serves as the axis of motion. The black cylindrical block in the center is the joint housing. The horizontal arm attached to the housing represents the moving link. The gray discs at the top and bottom act as ends, stops, or supports for the rod. We'll set the gray rod and the two discs as fixed components, while the joint housing and the arm will be dynamic. Next, we'll create a lock joint between the housing and the arm. Then, select the cylindrical joint option. Choose the first part, then the second. Define the axis position and direction. And click Create. Our cylindrical joint is now ready for testing. You can also right-click the cylindrical joint to configure its translational and rotational properties. Finally, we will create a ball joint. A ball joint provides unrestricted spherical motion by establishing a pivot point between components, making it well suited for modeling universal joints or multi-axis movement in robotic arm assemblies. We have prepared several components representing the ball joint. Set all device parts to dynamic. Next, connect the ball to the base using a lock joint. We can now define the ball joint itself. Specify the parts to be connected and the center of rotation. Use Snap Mode Gravity to accurately select the center point of the ball. Click Create to generate the joint. As in previous examples, use drag mode to test and observe the joint's motion. Additionally, you can right-click the ball joint to configure its elasticity properties. This concludes our overview of joint types and their use in RobotStudio's physics simulation. Thank you for your time. Please subscribe for more tutorials like this.